My name is Lothar, I'm a physicist, and I'm going to talk about a day in the life of an electron. Alright, let's get right to it. This is obviously an electron, the blue thing there. And it's a free electron, it's kind of single, in vacuum, and has a negative charge. Alright, now a proton comes along. The proton is also free, single, has a positive charge, so there's some obvious attraction going on here. And it's the second love story of the night after the lysosome and the I think. And I'm also going to skip over the steamy parts of this relationship, but stuff happens, and at the end of it, the electron ejects a photon that takes away some of the energy, and now the two of them are in a bound state. And the bound state is nothing else but an atom. So now we have an electron and a proton, they're bound together, and it's actually a hydrogen atom. There's also other atoms, more electrons, but those are for chemists. So I'm only going to talk about hydrogen atoms. But still though, what I'm going to hopefully convince you at the end of the talk is that even though this looks very simple, it's not. Okay? So what's happening, let's say the first effect, sometimes, the electron is going, and then it just, emits a virtual photon and then reabsorbs. So it talks to itself, kind of. And it's a virtual photon because it doesn't really exist, only for a very short time, and you cannot really detect it. And I probably should have mentioned that photon is what light's made of. Okay? Okay, how does a physicist look at this? They look at this so-called Feynman diagram. Obviously, the blue line is an electron, and obviously the green line is a photon. And what's going on here is that the electron, as it moves down in time, emits this virtual photon, and then it absorbs it again. Okay? So I'm an experimentalist. I don't know what the hell this means. So I'm just, break it down for myself and also hopefully for you. The way I like to think about this is, we have like a sad electron, it goes to bed at night. Next morning, it wakes up and it's kind of less sad. How did it achieve that? Well, this is a smart electron, right? So what it did is it wrote itself a motivational note, like, be negative, right? You're attractive, right? So really, this effect should not be called electron self-energy, but electron self-worth. It's a positive message I'm giving you. And, actually this effect increases the binding energy between the electron and the proton. So there's so many relations of metaphors in this, right? But I'm not going to talk about that. So that's self-energy. There's also another effect, so-called vacuum polarization. Vacuum is this white stuff around it. Turns out the vacuum is not empty. Sometimes, out of nowhere, a pair of particle and antiparticle disappears again, and again emits a virtual photon and talks to the electron. So the electron somehow feels that it's not alone, right? There's something else going on. It's really a lot of metaphors, right? Right, so this is kind of like the vacuum is a sea of particles. It's not empty, as you would maybe think. Okay, let's again look at this as from a physicist's point of view. Again, this kind of Feynman diagram, electron is moving along. Then suddenly, out of nowhere, this particle-antiparticle pair appears very briefly, disappears again, but it leaves a trace. This photon, which talks to the electron. So the electron feels there's something going on, and then a slightly less bound electron is left over. Again, what the hell does this mean? One way to think about this is electron is just minding its business, just kind of doesn't want to be bothered. And I'm going to move over there now because you guys are neglected all the time. And then unexpected stuff happens, and then it stays slightly less okay. I don't know how many of you take the subway, but I feel like pretty good analogy is like you're taking the subway and you're super crowded, and then suddenly there's a penguin playing the drums. It happens to me all the time, right? And this is the electron. He's not having any of it. I mean, yeah. So this decreases the attraction of the proton electron because it's just kind of strain on the relationship. All right. I feel like now you guys are experts on atoms. So I'm just going to quickly recap it for you. So this is how the atom looks like if you don't consider all this stuff, like 100 years ago, whatever. Then some smart guy comes along and says, actually the electron is relativistic, it's moving really fast, which is clearly seen here by, it's kind of smeared out. I did those myself, by the way. Also, the proton is also moving, it's more and more complicated. Also, the proton is actually relativistic, so it's also moving really quickly, clearly visualized here. And the rest of the stuff you already know, right? So there's the self-energy, there's the vacuum polarization, there's 2 photon corrections, 3 photon corrections, radiative recoil corrections, which you already know, nuclear self-energy, polarizability, and of course nuclear size. And for those of you who are a bit slower, I'm just going to have it go through once more, so you can familiarize yourself with the equations. Okay. So Now hopefully I've convinced you it's a mess, right? But that's our best guess of what's going on. That's our best guess of how the atom actually, what describes the atom, okay? And this mess has a name, it's called quantum electrodynamics. And actually it's a super successful theory. How do we know that? It's because we test it, okay? We test if this is true. And that's where I come in, so that's me, in the lab. And I'm working on my laser there, and my laser is a source of photons. What I'm going to do is, I'm going to shoot a photon onto this atom, okay, it's a real photon, okay? And I'm going to make this photon have just right enough energy to just break these two guys up, okay? Just right amount of energy. So what happens is the photon interacts with the electron, and the proton is gone again. It's a single electron again. I don't do this because I like to break up relationships. I do it because I know what the energy of the photon was. The photon just broke these two guys up, so I know what the binding energy between the two of them was, okay? So that's the idea of laser spectroscopy, to measure these energies. And it turns out we can actually do it pretty well. That's one of our recent results. That's 13 digits precision, and with this we test the theory. I'm not sure if you're familiar with kilohertz, so I converted to some more familiar units. It turns out this is 0.24 zeros, 173, 173, 498, 352, 47, plus minus 65. There's some uncertainty, big max. It's pretty small, meal, but electrons are also pretty small. This is actually serious science, right? So if you want to, this is an actual paper, but not in big mac units. I can do the conversion for you. Yeah, I think that's it. Thank you.